Section 1. The most powerful question in the universe. Have you ever looked up at the night sky and wondered what's really out there? Beyond the stars we can see, beyond the galaxies we can photograph, what lies in the deepest, darkest corners of the cosmos? What if I told you that the most destructive objects in the universe might also be the key to understanding creation itself? These objects are so powerful they can tear a star apart, yet so mysterious they challenge everything we think we know about space and time? They are places where the laws of physics as we understand them simply break down, ceasing to exist. The journey to understand them is one of the greatest adventures in all of science. If you find the universe as fascinating as I do, make sure you subscribe to keep exploring these cosmic mysteries with us. Now, let's get started. For centuries, we thought of gravity as a simple force pulling things together. Isaac Newton gave us equations that worked perfectly for planets and apples. But then a new mind came along, Albert Einstein, who saw gravity differently. He imagined space and time as a single fabric, a four-dimensional sheet called spacetime. He proposed that massive objects don't just pull on things. They warp and bend this cosmic fabric around them. This radical new idea set the stage for one of the most bizarre predictions in history. Einstein's equations of general relativity, published over a century ago, held a secret. They predicted that if an object was massive enough and squeezed into a small enough space, it could bend spacetime so much that it would literally punch a hole through the fabric of reality. At first, even Einstein was skeptical of this idea. It seemed too strange, too extreme to be real. A place with gravity so strong that nothing, not even light, could escape its grasp. For decades, this idea remained a mathematical curiosity, a ghost in the machine of physics. But as our telescopes grew more powerful, we started seeing things we couldn't explain. In this video, we're going on a journey to the edge of reality and perhaps beyond. We will explore what black holes truly are and how we know they exist. We'll ask the chilling question: what would happen if you fell into one? Then, we will venture even further into the theoretical unknown, discussing their hypothetical opposites, white holes, and the possibility of wormholes connecting different parts of our universe or even bridging to other universes entirely. Finally, we'll tackle the mind-bending idea that our own universe might exist inside a black hole. I'll break it all down step by step, so let's dive in. Table of Contents. Part 2, Act 1. What is a black hole? 1. The ultimate cosmic prison. 2. How to build a black hole. 3. The point of no return. 4. Catching a cosmic ghost. So, what exactly is a black hole? Is it some kind of cosmic vacuum cleaner, sucking up everything in its path? Not quite. But the truth is even more fascinating. A black hole is a region in space-time where gravity is so incredibly strong that nothing can escape its pull. Absolutely nothing. It's not a hole in the traditional sense, but rather a massive amount of matter compressed into an impossibly small space. Imagine taking a star many times more massive than our Sun and crushing it down into a sphere just a few miles across. The result is an object with such immense density that its gravitational field becomes a one-way street. Anything that crosses its boundary is trapped forever. The name black hole is perfectly descriptive. They are black because they don't emit any light of their own. Any light that gets too close is pulled in, never to be seen again. Think of it like this. On Earth, if you throw a ball into the air, it comes back down. If you could throw it fast enough, at about 25,000 miles per hour, it would escape Earth's gravity and fly off into space. This speed is called the escape velocity. For a black hole, the escape velocity is greater than the speed of light. Since nothing can travel faster than light, nothing can escape. This isn't just an object, it's a fundamental warping of reality itself. Remember how Einstein described gravity as a curvature in the fabric of space-time? A black hole takes this concept to its absolute extreme. It's a place where the fabric is bent so severely that it essentially closes in on itself, creating a pocket of space cut off from the rest of the universe. It's not a solid surface you could stand on, but a region defined by its overwhelming gravitational influence. Anything that ventures too close, whether it's a planet, a star, or a beam of light, is destined to fall inward. on a journey to the very center of this cosmic anomaly. But if they are completely black and don't emit anything, how could we possibly know they exist? How do you find something that is, by its very nature, invisible? It's a bit like trying to find a black cat in a pitch-black room. You can't see it directly, but you might be able to detect its presence by how it interacts with its surroundings. Astronomers have become cosmic detectives, looking for the telltale clues these invisible giants leave behind as they exert their immense gravitational power on the space and matter around them. We'll explore these clues, but first, let's understand how the universe even creates such monstrous objects. Section 2. How to build a black hole. So where do these cosmic behemoths come from? Can any old star become a black hole? The answer is no. It takes a truly massive star to end its life in such a spectacular and extreme fashion. Throughout its life, a star is in a constant battle with itself. The immense heat and pressure from nuclear fusion in its core push outward. The crushing force of its own gravity pulls inward. For stars like our Sun, this is a balanced fight that lasts billions of years. But for stars at least 20 times more massive than our Sun, the ending is far more violent. When these giant stars run out of nuclear fuel, the outward push from fusion suddenly stops. With nothing to counteract it, gravity wins catastrophically. The star's core collapses in on itself in a fraction of a second. That implosion triggers an unimaginably huge explosion, a supernova. The outer layers are blasted into space, creating glowing nebulae. But what happens to the core? If the remaining core is massive enough, about 3 times the Sun's mass or more, no known force can stop its collapse. The core crushes down, smaller and denser. It shrinks past the neutron star stage. The collapse keeps going until mass is compressed into a point of theoretical, infinite density. This is how a stellar mass black hole is born, from the corpse of a giant star. It turns a brilliant source of light into a perfect trap of darkness and gravity. It's the ultimate transformation from a beacon of light to an abyss. These aren't the only kinds of black holes. Astronomers have found supermassive black holes, millions to billions of suns. We find them in the centers of most large galaxies, including the Milky Way. How did they get so big? We're still piecing that together. They likely started small, maybe from the first generation of massive stars, and grew over billions of years by swallowing up gas, by swallowing up dust, by swallowing up stars, and even by swallowing up other black holes. They are the cosmic anchor around which entire galaxies revolve. Section 3. The point of no return. Now that we know how black holes are formed, let's talk about what defines them. What is the boundary that separates a black hole from the rest of the universe? Scientists call this boundary the event horizon. It's not a physical surface you could touch. You wouldn't feel a bump as you crossed it. Instead, it's a point in space, a threshold. It is the literal point of no return. Once you cross the event horizon, the pull of gravity is so strong that you would need to travel faster than the speed of light to escape. Since that's impossible, your fate is sealed. Think of it like being in a boat on a river that flows towards a gigantic waterfall. Far upstream, the current is gentle. You can easily paddle against it and go wherever you want. As you get closer to the waterfall, the current gets stronger. You have to paddle harder to keep from being pulled in. Eventually, you reach a point where the water is moving so fast that no matter how hard you paddle, you can't stop yourself from going over the edge. That point, where the river's current is faster than your maximum paddling speed, is like the event horizon. It's the moment your future is decided for you. And what lies at the very heart of the black hole, beyond the event horizon? According to Einstein's theory of general relativity, all the mass that falls into a black hole gets crushed into a single point with zero volume and infinite density. This theoretical point is called the singularity. Here, at the singularity, our current understanding of physics completely breaks down. The laws of space and time as we know them cease to make sense. It's a place where gravity becomes infinitely strong, and space-time becomes infinitely curved. What really happens there is one of the biggest mysteries in science, likely requiring a new theory that can unite gravity with quantum mechanics. So, a black hole has two key parts. First, the event horizon, the outer boundary, the surface of the black hole from which escape is impossible. The size of this sphere, known as the Schwarzschild radius, depends on the black hole's mass. The more massive the black hole, the larger its event horizon. Second, hidden deep within this horizon is the singularity, the central point where all the mass is concentrated. While we can mathematically describe the event horizon, the singularity remains a place of pure mystery, a point where our equations give us only infinities, signaling the edge of our knowledge. Section 4. Catching a cosmic ghost. How can we be so sure black holes exist if they're invisible and their singularities hidden? Do we have any real proof? The answer is a resounding yes. We can't see black holes directly, but we see their effects on stars and gas. One of the most compelling pieces of evidence: stars orbiting nothing. At our Milky Way's center, astronomers tracked stars for decades at very high speeds. Those stars whip around an unseen central point. Measuring their paths and speeds lets us use Newton's laws of gravity and Einstein's general relativity to calculate the mass they orbit. The result: over 4 million solar masses inside a region smaller than our solar system. Only one object fits that description: a supermassive black hole, Sagittarius A. This gravitational dance is smoking gun evidence. We also see black holes by watching them eat. A nearby star or gas cloud can have material pulled away by the black hole's gravity. The material forms a flat, spinning accretion disk around the hole. Friction heats the disk to millions of degrees. The hot disk glows in X-rays and other light, which telescopes detect. In 2019, the Event Horizon Telescope achieved a historic milestone. A global radio telescope network acted like an Earth-sized observatory. They imaged the black hole at the center of Messier 87, 55 million light-years away. The image shows a dark shadow encircled by a lopsided ring of glowing gas. We finally saw the shadow of a cosmic giant, a stunning confirmation of Einstein. Table of Contents, Part 3, Act 2. Spaghettification and the Journey In. 1. A one-way ticket to oblivion. 2. The ultimate stretch. 3. A tale of two clocks. 4. The view from the edge. So, we've established that black holes are real. We know how they're made, and how we can find them. This naturally leads to a very personal and perhaps terrifying question. What would happen if you fell into one? Let's imagine you're an intrepid astronaut on a mission to explore one of these cosmic mysteries up close. You decide to take the plunge. From a safe distance, your spaceship cuts its engines, and you begin the long, silent fall toward the event horizon. What would you experience on this one-way journey to the point of no return? As you drift closer, the first thing you'd notice isn't the black hole itself, but the stars around you. The black hole's immense gravity acts like a powerful lens, bending the light from distant stars and galaxies. The star field would appear distorted and warped, with multiple images of the same stars appearing in different places. The black disk of the event horizon would grow larger and larger in your view, eventually dominating your vision. It would be the blackest black you could ever imagine, a perfect circle of nothingness set against a swirling, distorted backdrop of the cosmos. The journey inward is surprisingly peaceful at first. In space, there's no air resistance, so you wouldn't feel like you're falling at all. You would be in a state of perfect freefall, floating weightlessly inside your spacecraft. But a hidden force is about to make its presence known. It's the reason we have tides in our oceans. The moon's gravity pulls slightly more strongly on the side of the Earth facing it than on the side facing away. This difference in gravitational pull stretches the Earth. Near a black hole, this same effect, known as a tidal force, is amplified to an unimaginable degree. What happens when these tidal forces take hold? Let's imagine you are falling feet first toward the black hole. The gravitational pull on your feet will be immensely stronger than the pull on your head. This difference in gravitational force would create an incredible stretching sensation. The process has a rather vivid and descriptive name: Spaghettification. Your body would literally be stretched out into a long, thin strand of atoms. The same force would also be acting horizontally. This would squeeze you from the sides at the same time you are being stretched. So you would be simultaneously elongated and compressed, funneled down into a thin stream of particles destined for the center, for a stellar mass black hole. These tidal forces are incredibly powerful. You'd be torn apart long before you ever reach the point of no return. But what about a supermassive black hole? Here, the story is different. For a truly giant black hole, the tidal forces at the event horizon could be so gentle that you could cross it without feeling a thing. You could slip past the point of no return completely intact, blissfully unaware that your fate has just been sealed. Let's say you've chosen wisely and are falling toward a supermassive black hole. You pass the event horizon unharmed, but something very strange is happening to time itself. This is another prediction of Einstein's theory of general relativity. Gravity warps time. The stronger the gravity, the slower time passes. This effect is called gravitational time dilation. It's not science fiction. The GPS satellites orbiting Earth have to constantly adjust their clocks because time runs slightly faster for them in their weaker gravitational field than it does for us down here on the surface. Near a black hole, this effect is taken to the absolute extreme. For you, the astronaut falling in, time would seem to pass normally. You could look at your watch, and it would tick away 1 second at a time. But what would your friends, watching from the safety of their spaceship far away, see as you fall in? They would witness something completely different. As you get closer to the event horizon, they would see your clock ticking slower and slower. They would see your movement slow. As you reach the event horizon, from their perspective, time for you would grind to a complete halt. To the outside observer, you would never actually cross the event horizon. They would see your image frozen at the boundary, getting dimmer and redder until you faded away into nothingness. So, who is right? You or your friends? The answer from relativity is that both of you are right. Your experiences of time and space are relative to your own position and motion. You would experience your demise at the singularity, while your friends would witness you being eternally frozen on the brink. This phenomenon gives rise to a fascinating idea known as the holographic principle. Some physicists propose that information about everything that fell in isn't lost at the singularity. Instead, it might be encoded on the two-dimensional surface of the event horizon. This idea attempts to solve the black hole information paradox. Quantum mechanics says information can never be truly destroyed. Classical black hole physics seems to say it is destroyed. Now switch back to your perspective. Looking back, you can still, in principle, see the outside universe, but the view would be incredibly distorted. The entire future history of the external universe flashes by in a sped-up movie as you fall. Looking forward is the singularity. It's no longer a place in space, but an inevitable destination in time. The fabric of reality is collapsing and carrying you with it. Tidal forces grow exponentially. Spaghettification becomes your inescapable final experience. Your journey in is complete. It seems like a one-way street, a final destination. But what if it isn't? What if physics in its beautiful symmetry demands an opposite? If a black hole is a place where you can only fall in, could there be a place where you can only fly out? We call these hypothetical objects white holes. A white hole is, in essence, a black hole running backward in time. While a black hole pulls everything in, a white hole is a region that violently spews matter and light out, and which nothing can enter. It's a perfectly valid mathematical solution, but it raises a huge question. If they are possible, where are they? Unlike black holes, we have never seen anything in the universe that behaves like a white hole. One intriguing, though highly speculative idea is that the Big Bang itself might have been a kind of white hole. It was a moment in time when all the matter and energy of our cosmos erupted from a single, impossibly dense point. The mathematics that describe black holes and white holes hold another, even more tantalizing secret. A shortcut through spacetime called an Einstein-Rosen bridge. A wormhole. It could, in theory, connect two vastly distant locations in our universe. Step into one in the Milky Way, emerge moments later in Andromeda, millions of light years away. But the model has serious problems. The Einstein-Rosen bridge is incredibly unstable. The throat would collapse almost instantly. Not even a single photon could make it through, let alone a spaceship. If you jumped in, you wouldn't emerge in a distant galaxy. You'd hit a dead end and be crushed at a singularity. Is that the end of the line for wormholes? Not quite. To stop the wormhole collapsing, you'd need to thread it with a substance that has negative energy, negative mass. We call this theoretical material, exotic matter. It would have anti-gravitational effects. If you had a ball of it and you pushed it, it would accelerate toward you instead of away from you. A lump of exotic matter would fall up, not down. We have never found or created such matter. Some quantum effects can create tiny regions of negative energy density, but we have no idea how to gather enough to stabilize a human-sized wormhole. And then there's time travel. Relativity shows wormholes could act as time machines, connecting two different moments in time. That opens a Pandora's box of paradoxes, like the classic grandfather paradox. If wormholes could exist, where might they lead? What if they connect to somewhere else entirely? The multiverse hypothesis suggests our universe might be one bubble among many. Now we arrive at the most mind-bending question of all. We've been looking out at black holes in the cosmos, but what if we've been looking in the wrong direction? What if our entire universe, every star, every galaxy, everything you've ever known, exists inside the event horizon of a black hole? Could it be that we are living inside one of these cosmic giants? This idea proposes that our universe is the interior of a black hole that itself exists in a much larger parent universe. Think of it like a set of Russian matryoshka dolls, with universes nested inside of other universes. The initial spark for this idea comes from a surprising mathematical similarity. The equation that describes the expansion of our universe looks remarkably similar to the equation that describes the space-time inside a black hole. If we are living inside a black hole, what would that feel like? Would we feel crushed by gravity? The surprising answer is no. It would feel exactly like the universe we currently live in. The expansion of our universe fits neatly into this picture. In the black hole cosmology model, this expansion isn't just matter flying apart. Instead, the fabric of space-time could be collapsing inward toward the central singularity. From our perspective inside, we perceive everything moving away. This model offers a potential solution to the singularity problem, and also addresses the flatness problem, like a giant balloon appearing flat to a tiny ant. One key prediction concerns how our universe rotates. If the black hole was formed from the collapse of a spinning star, our universe should have inherited that spin. We should see a slight preferred axis of rotation on a cosmic scale. Another clue could be the cosmic microwave background. Observations reveal strange large-scale anomalies, including a mysterious cold spot that seems statistically unlikely. These findings are highly debated. If confirmed, this would seriously challenge the standard model. Still, none of this is conclusive proof. The jury is out. The path forward lies in finding a more fundamental theory of physics. A complete theory of quantum gravity could give us a definitive answer about what truly happens inside a black hole and at the moment of the Big Bang. We have traveled to the very edge of human understanding. We learned they are regions of space-time where gravity is so dominant that nothing, not even light, can escape. We have seen the overwhelming evidence for their existence. We then took the ultimate plunge. We discovered spaghettification, time warps, creating two stories, one for the falling astronaut and one for the distant observer. We then ventured into wilder theoretical shores, white holes, wormholes, gateways to other universes. Finally, we asked if our observable universe might be the interior of a black hole. So, we returned to the question that started our journey. What lies in the deepest, darkest corners of the cosmos? The honest answer is that we are still searching. They are the place where our two greatest theories, general relativity and quantum mechanics, collide. A new, deeper understanding of reality must emerge from that collision. The journey to understand these objects is a perfect reflection of the scientific process itself. So, keep wondering, keep asking questions, and never lose your sense of awe for the grand, mysterious, and beautiful cosmos we call home. The next great cosmic discovery could be just around the corner, waiting to once again change everything we thought we knew about our universe and our place within it. The journey truly has no end.